Good morning, everyone. Hi, I'm Shubhayan Sarkar. So currently I'm working as a postdoc with Dr. Stefano Pironio in Brussels. So today I will be presenting on the topic self-testing composite measurements and bound entangled state in a unified framework. So just to be clear, it's like more from a theoretical and mathematical perspective, but I will try to make it as simple as possible. So to begin with, let's try to understand what is meant by device independent certification or self-testing. So now suppose that I have been given a device from a manufacturer and it promises to produce entangled photons. So now the question is, how should I verify that this device actually performs the way that it is supposed to, or should I just blindly trust the manufacturer? Now, one possible way is that I can break this device and I can check the source, but then that's not a good idea. So I want the way to know some properties about this device without having any information about the underlying system of this device. So what we can do is we take the two arms of the entangled sources and then put them in specially separated regions and then do some measurements of them. Now it turns out that if you forget about what measurements you're doing, but just look at the correlations which are being generated from these measurements or this joint probability distribution. So then, and if it violates some Bell inequality, then we can say that the device actually produces entangled photons. So what is meant by Bell nonlocality or Bell inequality is, suppose that I have an Alice and Bob who are located in two separated labs. Now, each of them get to choose two inputs freely, which are like independent from each other, and each of their measurement choices give like two outcomes each. So I do not know what is going on inside this device, but just that there are some buttons, and Alice and Bob, they both just press some buttons and see some outcomes, and at the end of the experiment, they just look at the joint probability distribution of like probability of getting outcome A and B given the measurement AX of Alice and BY of Bob. Now, if you are restricted to quantum theory, you know that these probabilities can be calculated using the bond rule, which is like the trace of the shared, the state shared between Alice and Bob and the measurement elements of Alice and Bob. So now the simplest Bell inequality is the Clauser-Horner-Simony-Holt inequality. So Clauser, as you may know, that received the Nobel Prize this last year for discovering this Bell inequality. So basically, it gives you an experimental test of showing that nature is truly non-local, or there are no local hidden variable explanations of some quantum correlations. So now, simply speaking, this is like a sum of 4 terms. And each of these terms represent the expectation values of when Alice chooses an observable A1 and Bob chooses an observable B1. So now all of these things can again be expressed in terms of the probabilities, which I showed before. So from the experiment, you get the probabilities, and from the probabilities, you can calculate these expectation values. And then it turns out that if this inequality is violated, then it means that there is some non-locality in the systems. And it turns out that there are some quantum states and measurements which will violate this inequality. So in fact, the maximum that you can go, as was shown by Cyrelson, is 2√2. And you can get to this value using the maximally entangled state. And Alice performs the Pauli sigma Z and Pauli sigma X, and Bob performs a linear combination of them. So now let's call them like some ideal realization, which will give you this value root. Now we consider a reverse problem. So suppose now that I did this Bell test, I did this experiment, and now I see a value 2√2. Now the question is, from this value 2√2, can I conclude some properties about this device? So it turns out that yes, you can. And the technique is known as self-testing. So this is in fact the most strong. So this is the strongest device-independent certification scheme. So, and it was introduced in 1998 by Mayers and Yao. So basically, we are given a device, we can predict the state and the measurements on which this device operates by only looking at the correlations which are being generated by this device. So how is it done? So first, a Bell inequality needs to be maximally violated by a state and some measurements. And this is not the only way, but the majority of the protocols follow this way of self-testing. And then if they are unique up to some local unitaries and some presence of junk state, then the statistics are enough to tell me what are the states and the measurements. So for example, again, going back to the CHSH case, let's say I attain a value 2√2. So it turns out that getting a value 2√2 of this inequality, you touch the quantum set or the set of probabilities which are achieved using in quantum theory at a single point. And then you can show from there that up to these local unitaries, your state is the maximally entangled state. And up to these local unitaries, the measurements of Alice and Bob are the ones that I showed before, the ideal ones. So why is it important? So now when we are seeing the rise of quantum technologies like quantum cryptography, like random generation, like quantum random generators, and even like quantum computers, although they are a bit noisy now, but still. So it's necessary now to certify whether these devices are doing what they are supposed to do, and there is no glitches or no way they are performing some different operations than what they are supposed to do. So now self-testing is a way to verify that actually, yes, it is doing what it's supposed to do, and there is no other control over this device. And then a device-independent certification provides a natural framework where some of the properties can be known about this device by only looking at the correlations. And coming back to this talk, so in this talk, we want to self-test like composite measurements. I will come to what is meant by that, and mixed states. So there are very few schemes which do this kind of self-testing, because in the standard Bell scenario, you cannot self-test mixed states, and neither you can self-test composite measurements using in the standard Bell scenario. So before going to the results, let us recall some of the assumptions that go into this. I mean, these are quite natural. Like, for instance, the devices are governed by quantum theory. Then the source generates independently and the same state in each round of the experiment. This is also known as the IID assumption. And then the measurement of all the parties remain consistent throughout the experiment. So what is meant by composite quantum measurements? So now it is known that in quantum theory, states and measurements are dual of each other. So if you pick up a state, and there is always a corresponding measurement which will give you the corresponding state. Now, because you know that there are composite quantum states, there are composite quantum measurements. So these measurements are acting on like composite Hilbert spaces. Now, basically, there are these four major types of composite quantum measurements. One is the local measurements, like just locally different measurements are acting on different systems. So, and the second is what is known as the non-locality without entanglement. So, for instance, if I have a set of projective measurements which are given by this, and each of these elements are product states, as you can see here. But it turns out that these set of 8 vectors, which are completely orthogonal and product, but they cannot be distinguished using local operations and classical communication. So in a way, it's kind of notion of non-locality, but there is no entanglement in the system. Next is what is known as the unextendable product basis. So, so basically, it's like you have some set of product vectors, but then there does not exist any other product states which can be able to complete this basis. So the last element is like identity minus the sum of these elements, and this is like mixed. It's kind of like a POVM. And then the last measurement is the negative partial transpose entangled basis. For instance, you can consider the Bell basis, or this is known as the GHZ basis. So each of these elements are like maximally, I mean, each of these elements are entangled and are pure. So our aim here was to self-test these exotic kind of measurements, which cannot be self-tested in the standard Bell scenario. So the scenario that we considered is like this, that we have a quantum network. These wavy lines represent independent sources. There is a central party which performs like a joint operation on all these three independent systems. And then there are these external parties, and they perform single measurements on the single system that they receive from these sources. For our case, we choose like two inputs for these external parties. The central party has like 8 outputs, and all of them have like 3 inputs. So, and then we will self-test all the 4 types of measurements in a single scheme. So let's focus now on the case when Eve chooses, like the central party Eve chooses the input 0. Now what we say that, let's say that I choose that Alice, Bob, and Charlie, or these external parties, they see the maximum violation of these Bell inequalities that we constructed, and along with a statistical test of this form. So again, as you can see, these are the expectation values. I won't go much into the mathematical details, but let's say these are some statistical tests, and you satisfy them, and then it turns out that because of each measurement, some post-measurement states are being prepared with the external parties, and now each of them need to violate some Bell inequality. And from there, what you can conclude is that up to these local unitaries, these independent sources are certified to produce like maximally entangled state, and Eve's measurements are certified to be the GHZ basis, as I explained before. And the measurements of the external parties are these linear combinations of Pauli sigma Z X, and for some other parties, these are like just Pauli Z X and Y. So coming back to the second input of Eve, there we show that, okay, we choose another statistical test, and along with the test for the previous input, it turns out that it's enough to tell me what up to these local unitaries, the measurement of the second measurement of Eve is this non-locality without entanglement basis. And then finally, we are also able to self-test unextendable product basis in this same scheme. So, so the statistics involved for this were a bit complicated, so you can check out the paper. So I didn't mention it here, but yeah, so we have found those statistics, and again, with the statistics for the first input of Eve, you can certify that the third measurement of Eve is the unextendable product basis up to these local unitaries. Now, interesting consequence of this is that this network allows us to certify a bound entangled state, which is being shared between these two parties. So in the standard Bell scenario, you cannot certify mixed entangled states. So this is in fact the first scheme which where a mixed entangled state can be certified. And for this, again, we suppose that all the measurements and the states are already certified. and then Eve now just broadcasts her outcome, and then the states which are being prepared by these prepared on these external parties are these bound entangled states. So coming to the end of the talk, so basically our approach enables to self-test like exotic kind of measurements. So in particular, the non-locality without entanglement. And then we also utilize like the minimum number of parties, minimum number of measurements per party, which is 2. So you cannot improve this protocol in any other way. Then it allows for a simultaneous self-test measurement, which is constructed from an unextendable product basis. And then we are also able to certify mixed entangled states. So if you want to check out the details, you can visit this archive link. So that's it from my side. Thank you.
Okay, thank you very much. We have one question. Could you please mention why the Bell tests don't allow self-testing for mixed states?
Yeah, because so in the Bell scenario, there is no restriction on the dimension. So if you have a single source, you can always purify that source and you get, in fact, a pure state. So even if, let's say that there is some set of correlations which are being, some maximal set of correlations which are being achieved by this mixed state, but then there is a purification of the state which will also achieve the same correlations. So in a way, you can never uniquely certify that your state was this mixed state. So, but if you consider these quantum networks, and because we have this idea of like independent sources, and because of this physical assumption, it allows us to certify these mixed states. Like in a nutshell, we can say something like this.
So you cannot use the measurements because you can use purification? I don't understand. I mean, you can.
Yeah, so I mean, from self-testing, it allows us that if you see some correlations, then up to these equivalences like local unitaries and this junk state, can you identify the state or not? So because you have a mixed state, you can always purify this state. So then the mixed state will also get this, I mean, to saturate this correlation, the pure state along with the mixed state will give you the same statistics. So in a way, you cannot uniquely identify this mixed state from there.
Okay, I think that there is a follow-up to this question. Would it work if we fix the dimension?
Maybe. I mean, but that's, I mean, if you cannot fix the dimension in a way, like, so then it will be like a device dependent case, because fixing the dimension is a very strong restriction. In a practical scenario, I can never know what the dimension of my system really is. So it could be like attached to a lot of different degrees of freedom, and I cannot exactly say what the dimension is. But if there is a way to conclude before the experiment that, okay, the dimension of my system is 2 or 3, so then I guess we can certify mixed states.
If we fix the dimension, yes?
Yeah.
Okay, because for example, in some schemes for communication, you have to, I mean,
yeah.
that there is
like,
some, restriction on the dimension, because otherwise
exactly. Yeah, so in those prepare and measure, like I guess you're talking about those prepare and measure scenarios, and there you have this restriction on dimension, but again, those are not fully device independent schemes. So it's like those are also known as like semi-device independent way of certifying states and measurements.
Okay, another question, and it is about entanglement measures. There are measures as the concurrence and others that quantify the entanglement of a mixed state of 2 qubits. There are some ways to quantify how entangled state is in this. Okay, I think the question is if it can be used as a measure of entanglement. I mean, your scenario, your scheme can be Can you transform it into a measure of entanglement?
Not exact. So I haven't thought about this, but at present this scheme is like really specific. So it works only for a particular state and particular set of measurements. So for instance, it's like these non-locality without entanglement is a particular basis that we choose again for this GHZ basis. It's like a particular basis. It's not like it's true for any general set of states and measurements. So I don't see right now how it can be done, but maybe it's possible.
Okay, I hope that was the idea of this question, because I don't understand it correctly. Okay, thank you very much.
Yeah, thanks a lot.
Again,